Hello everyone. In this video, we will try to learn linear algebra from basic to advanced, right? And I will try to give you real life examples like everyday buy and sell scenarios so that you can relate with the things easily, okay? So let's start. So first of all, we need to understand what is linear equation. So to understand linear equation, I will try to give you an example, right? So imagine you take a taxi ride. Most taxi service have a fixed starting charge plus an additional charge per kilometer traveled. Okay, so let's say the base fare is $5 and charge per kilometer is $2. Okay, so if you travel like 10 kilometers, then 10 into 2, 20 plus 5, 25 would be the total price, right? So this equation, if you see this equation, y equals 2x plus 5 or 5 plus 2x, however you say. Okay, so here 5 would be the constant. 5 is constant, 2 is also constant, x is variable, right? X can change. So it follows the standard form y equals to mx plus b. So these types of equation is, this equation is a linear equation, right? So sometimes you can pause the video and if you want you can read the screen, right? Okay, explain linear algebra with real life example. So here we say, see, linear algebra deals with vectors, matrices, and systems of linear equations. It's a powerful tool used in many fields like physics, economics, computer graphics, machine learning, and more. So real life example of linear algebra. So let's say you want to get from point A to point B using GPS. So I don't want to, spend more time reading this because you can read this, okay? So what we will have to learn, this vectors, vectors, matrices, and a system of linear equations. Okay, so what is vector actually? We can try to understand what vector. Okay, so let's say in the simplest sense, a vector can represent direction and distance. Okay, so in our, if you want to relate with everyday thing, a real life example, you can so we can relate vector as direction and distance. Okay, so here you say the vector a equals 3 4, okay, represents traveling 3 units east and 4 units north. So let's say wherever I'm sitting now, I traveled 3 kilometers east and 4 kilometers north. Okay, uh, so uh, so there would be a specific point. Okay, vector b 1 to represents traveling 1 unit east and 2 units north. So you can combine these vectors to get a new direction. Okay, so values of x-axis 3 plus 1, values of x-axis would be added, and values of y-axis will be added separately. Okay, so 4 6 is my new you know uh, current position, right? So when you add this thing, 3 plus 1 4 plus 2, this is vector addition, guys. Okay, so we can subtract as well. Okay, so subtraction is the reverse thing, you can say. So 3 minus 1 4 minus 2, this would be the subtraction, right? So you can see here vector subtraction, a minus b, ax minus bx, ay minus by. So I hope you understand what ax and bx is. Ax is 3 and bx is 1. Okay, so you see 2 2, and we need to understand some other operations of vectors as well. Scalar multiplication. Okay, scalar multiplication is the next one. Multiplying a vector by a scalar scales the vector by the scalar. You multiply each component of the vector by the scalar. Okay, so we will try to understand what scalar multiplication is, and dot products, and some other things. But we need to understand where these things can be applied. Okay, so for the time being, just focus on the thing. Okay, focus on the definition and the formulas. Okay, so let's say if c is a scalar and a equals ax ay, then c into a, that means c into ax into c into ay. So both the values of a, x and y would be multiplied with c separately, right? So a equals 3 4, so scalar c equals 2. That means 2 would be multiplied with both 3 and 4. Okay, so 6 and 8. So this means you are stretching the vector to twice its original length. We will see where this can be applied in real life. Okay, And dot product, the dot product of two vectors results in scalar. It measures how much one vector goes in the direction of another vector. So maybe this, maybe now you may get confused, but when we discuss with real life thing, then you will understand easily. Okay, so a equals ax ay, b equals bx by, a dot b, that means ax dot bx plus ay dot by. So that means, guys, a equals 1 2, b equals 3 4. So we get, finally we get 11. Okay, 1 into 3 plus 2 into 4 equals 3 into 3 plus 8 equals 11. The dot product tells you how much one vector goes in the same direction as another. It's used in physics to calculate work and in computer graphics for lighting effects. Okay, so what is cross product actually? The cross product is only defined in the three-dimensional space and gives a vector that is perpendicular to both input vectors. Okay, so if you see here, a equals ax ay az, b equals bx by bz, so cross product is a cross b. So how it's calculated, guys? So ay dot bz, that means this one dot bz, minus az by. So this minus this into this, comma az into bx, that means, guys, az into bx, this one, this one and this one, minus ax bz. Okay, so middle one is middle one is not being considered here. Okay, so ax, after this comma, ax dot by, that means ax dot by, this one and this one, minus ay dot bx. Okay, so this is the formula, guys. Okay, so example, a equals 1 0 0 0 1 0. If we put these values here in this equation, then we get a dot b, a cross b equals 0 0 1. This means the cross product gives you a vector that is perpendicular to both input vectors. In real life, it's used in determining forces in physics like torque. Okay, so we have to understand another thing, that is magnitude of vector. So yes, we will understand where these things can be applied, but for the time being, just focus on the formulas. Okay, so magnitude of a vector, magnitude is like Pythagorean theorem. Okay, how we calculate uh, hypotenuse of a triangle. So this is the formula is being used here. Okay, so a equals 3 4. So that means, guys, when you see 3 and 4, 3 square plus 4 square, 9 is 9 plus 16, and so 25, root over 25 equals 5. So 5 is the magnitude of these vectors, right? Unit vector, a unit vector is a vector that has a magnitude of 1. To convert any vector a into unit vector, you divide each component of the vector by its magnitude. Okay, so u equals a divided by magnitude of a. Okay, so that means, guys, u equals 3 4 divided by 5. Okay, so 3 and 4 would be divided by 5 separately, as you can see here. So we get 0.6 and 0.8. This gives a unit vector in the same direction as a, but with a length of 1. Okay, so you can say in length of 1, what proportion of this represents. Okay, 0.6, and this is 0.8. Okay, out of 1. So why are these operations important? If you want, you can pause the video and read it. Okay, so now we will see the real life scenario, guys. Online store sales analysis using vectors. Okay, so imagine you own an online store that sells two products, smartphones and laptops. Each day you record the number of items sold and total revenue earned from both products as vectors. Let's use vector operation to analyze sales performance over multiple days. Okay, so let's say your sales data over 2 days are S1 20 10. That means 20 smartphones and 10 laptops you sold in day 1, and 25 smartphones and 15 laptops you sold on day 2, right? So these are the two vectors. So if you add them, vector addition, so S total equals S1 plus S2. That means, guys, 20 plus 10, 25 plus 15. So 20 and 25 would be added together, okay, because these are the data for smartphones. So 20 plus 25 equals 45, and 10 plus 15 equals 25 laptops, okay. So that's how we get the data for two different days, right? And scalar multiplication, okay, so where we can apply multiplication in real life, okay. So let's say each smartphone costs $300 and each laptop costs $800. So we represent these as a price vector, okay. So 300, 800. So now we will multiply it with their products, okay. So to calculate the total revenue for day one, we use scalar multiplication. So s1 dot p, that means guys, s1 is 20 smartphones into 300 plus 10 into 800. So this is the total revenue we get for day one, right? Okay. And for day one, your total revenue was $14,000, okay. So for day two, it would be 25 into 300. Okay, so now we can understand where scalar multiplication is applied in real life. These things are not difficult, guys. Things are really easy uh, if we relate with real life thing. Maybe in when we do job or a real life workplace, when we work in real life workplace, then maybe things might be little bit difficult, or um, but now we can understand with real life small things, so that we can at least get idea how things work, right? So you see a vector subtraction, so change in sales performance. To see how much sales increased or decreased from day one to day two, we subtract the vectors, okay. So if we subtract s2 from s1 from s2, so we get 5 5. So on day two you sold 5 more smartphones and 5 more laptops, okay, compared to day one. So we can guess from the simple calculation. So this is where we can apply vector subtraction, guys, okay. Dot products, so sales performance in a weighted scenario. Now let's assume your profit per unit for each product is $50 per smartphone and $200 per laptop, okay. So we made another vector here. So now if we just s1 dot profit, so 20 into 50 and 10 into 200, because profit for both the products is different, 50 and 200. So now we get the total result. So 3000 is the total profit for day one, okay. So it will be the uh, $4250 for day two, okay, according to the calculation. And now we will go for the magnitude, and we will try to understand where magnitude is applied in real life, okay. So the magnitude of a vector represents the total sales volume as a single value, okay. So s1 equals 20 square plus 10 square. This is for the day one. So if you calculate this, we get 22.36, okay. So the total sales force for day one is 22.36 units, a measure of combined sales of both products, okay. So you may say what this is actually, why we can where we can apply this, why this is important. You may think this, okay. So if you see the day two's data, okay, so this is the sales for day two, so 29.15. So if you compare 22.36 and 29.15, so we can easily say that in day two we did more sales activities, right? So without considering separate mobile and smartphones for 2 days, without considering separate mobile sales and I mean smartphone sales and laptop sales, okay, without considering them separately, we can with these values, after seeing these values, we can say that day two's uh, sales activity was higher than compared to day one, right? So this is where magnitude can come into action, guys. Pardon my weak English. My English is not good, but I'm trying to explain things with real life uh, scenario, so that we can actually relate with this thing. Okay, now we will see where we can apply unit vector. Okay, so if you see here, the unit vector shows the proportion of sales coming from each product. If you see here, U1 equals S1 divided by a magnitude of S1. So 2010 is the for day 1. So magnitude for this is this, right, 22.36. So if we divide separately, then we get 0.89 and 0.45, right? So what does this actually represent? uh, on day 1, about 89% of total sales were smartphones. Okay, so we can uh, from unit vectors we can say the percentage of each product sale. Okay, so this is where we may need uh, unit vector. About 89% of total sales were smartphones and 45% were laptops. Okay, so for day 2 we will get another data. Okay, so you see here. So on day 2, smartphone sales slightly decreased in proportion, while laptop sales slightly increased in proportion. The conclusion: in business and finance, vector operations help analyze sales trends, revenue, and profit in a structured way. These calculations are used in inventory management, financial forecasting, and sales optimization. Anyway, if you haven't got clear idea about these terms or operations, real life scenario for these operations, you can watch the video again. Okay, uh, or you can ask ChatGPT to give you some real life scenario and you can think. Okay, spend some time to think. So now I want to learn a matrices. It would be better if the examples from any buy and sell scenario are related to money or in this case too. Okay, so what are matrices? So let's have a read. Okay, let's say you own a store and sell three types of products, A, B, and C. You want to track the quantity sold and a profit per unit for each product and ultimately calculate the total profit based on the sales. Okay, so represent the sales data and profit data as matrix. Matrix 1, this matrix contains the quantity sold for product A, B, and C over 3 days. Okay, so you see rows represent the days, columns represent the products A, B, and C. Okay, 5, 3, 8, 10, 2, 5. So if you see the explanation on day 1, 5 units of A, 3 units of B, and 8 units of C were sold. Let's say shirt, pants, and maybe jackets. Okay, so 5 units of shirts, 3 units of pants, and 8 units of jackets. This is how you can put this. Okay, so on day 2, 10 units of A, 2 units of B. So this is the sales data for 3 days and 3 products, right? Matrix 2, this matrix contains the profit per unit for products A, B, and C. Okay, so 20, 30, 25. So these are the profits for each product. Okay, so now we are multiplying total profit for so 5 into 20, 3 into 20, 3 into 30, and 8 into 25, right? So in general we see these types of calculations in our textbooks, but we don't get idea why these things are used. Okay, sometimes. So you see here 5 into 20, 3 into 30, 8 into 25, 10 into 20. So this is how it's calculated, and finally we get the result: 390 for product A, 385 for product B, 435 for product C, right? So this matrix multiplication allowed us to quickly calculate the total profit for each day by using the sales data and profit per unit. Instead of manually calculating the profit for each product, the matrix multiplication provided a faster and more efficient solution. Okay, so how would it be represented if matrix was not there? I just curious to ask. Okay, so you can see here day 1, A equals 5, B equals 3, C equals 8. So profit per unit 20, 30, 25. It's just calculating manually, right? So 5 into 20, 100, 3 into 30, 90, day 2. So these things are being calculated manually and giving me the result. Okay, so matrix addition and scalar multiplication. Give me example like this again to explain them. So matrix addition, tracking weekly sales growth. Okay, so imagine you own a small store selling 3 products, A, B and C. You keep track of sales for 2 weeks. So week 1, product A you sold 10 units each day, product B sold 15 units each day, product C sold 20 units each day. So for week 2, you sold 12 units each day for product A, B 18 units and C 25 units. So if you represent here, week 1 sales 10, 10, 10, 15, 15, 15. So this is how it's being represented, right? So total sales would be 10. Okay, so 22, 33, 45 you can see here. Okay, product A 22 units, product B 33 units, product C 45 units. This shows how matrix addition has been analyzing cumulative sales over time. So scalar multiplication, calculating total revenue. Now suppose each product has a fixed price, let's say $5 for A, $5 per unit for A, $7 per unit for B and $10 for C. To find the total revenue for each product over 2 weeks, we multiply the total sales matrix by the price of each product. Okay, so 5 into 22, 7 into 33, 10 into 45. So total revenue would be 791. This example shows how scalar multiplication helps in quickly computing revenues or applying a fixed percentage change. Okay, and now we will see matrix multiplication and properties. Okay, so in real life we know we know the properties of multiplication, but in case of matrix we will see now. So matrix multiplication in a buy and sell scenario. So calculating a total revenue for multiple days. Okay, so you see here sales data as a matrix. The sales data can be stored in 3 into 3 matrix where rows represent the days, column represents the products. Okay, so 5, 3, 8, 3 products. Okay, A, B and C. So let's say 5 units of A, 3 units of B and 8 units of C. Okay, so on day 1 you should you sold 5 units of A, 3 units of B. Okay, so you can see here. So represent a price as a matrix. Okay, so the price of each product remains fixed. So you represent as a column matrix 20, 30, 25. So these are the same examples we are getting here. Product A 20 per unit, 30 per unit for B and C. So step 3, multiply the matrices. Okay, so if you multiply them, revenue would be like this. Okay, 5 into 20, 3 into 30, 8 into 25. So performing matrix multiplication, see here. Okay, so that means guys we get the result here. So matrix multiplication properties in this context, associative property, you can say A cross B, A into B inside the bracket and outside the bracket C. Okay, so this we know that associative property of multiplication, right? So that means guys if you consider 2 into 3 into 4. Okay, so however you count, however you do the operation, you will get the same result. A into inside the bracket B into C. So both side will give us the same result. Okay, so distributive property we know also about this one, A into B plus C. That means let's say this is A is 2, B is 3, C is 4. Okay, so however you count, however you calculate. Okay, so 3 plus 4, that means 7 into 2, that means 14. So if you do the same thing with like this. Okay, so 2 into 3 6 plus 2 into 4 8, so it will be 14 again. This is a distributive property guys. Okay, so non commutative property. So in this case order matters. Okay, so why this thing is different from arithmetic thing, or however we do with the normal calculation. Why is this different? We will see here, right? Why order is important in matrix multiplication? So unlike regular multiplication, matrix multiplication does not follow this rule. Why? This means changing the order of multiplication can give a completely different result of even be possible. Okay, example in buy and sell scenario, let's take 2 matrices. Sales matrix A represents units sold per day for different products. Okay, so price matrix B represents price per unit for each product. So let's say this one 538, whatever we saw before, and B is, this is the price. Okay, so the total revenue, if you multiply these, in this way we can get the result. Okay, so if you change the order, B comes first and in A last. Okay, so how you can do the thing now 25, so how? Okay, so this is why, because this thing is behaving as an array, a collection of datas. Okay, so many datas uh, are being presented inside the third bracket, so it's not possible to consider this as a normal calculation, normal normal multiplication, right? For multiplication to be possible, the number of columns of the first matrix must match the number of rows for the second matrix. Okay, this is the thing. But here B has one column and A has 3 rows, so multiplication is not defined. Okay guys, now we will understand transpose, inverse and determinant of a matrix. Okay, so let's start from the transpose. Okay, so the transpose of a matrix flips its rows and columns, you can say. Suppose you have sales data for 3 products P1, P2 and P3, sold in 2 stores, S1 and S2. So each row represents a store and each column represents a product. So 5, 3, 8, 10, 2, 5. So that means store 1 sold 5 of P1, 3 of P2 and 8 of P3. This is the for 5, 3, 8 for the store 1. Okay, for store 2, sold 10 of P1, 2 of P2 and 5 of P3. So transpose of sales matrix. So now let's swap rows and columns. Okay, so let's name it ST and 5, 10, 3, 2, 8, 5. So now each row represents a product and each column represents a store. Okay, we just swapping. So 5, 3, 8, this is for S1 now, that means store 1, and 10, 2, 5, this is the store 2 guys. Okay, so 5 and 10, if you consider this one, 5 and 10, these are the data for P1, right, product 1, and 3, 2, these are the for product 2, you can say. So why is it useful? Instead of asking how many units did each store sell, you can now ask how many units of each product were sold across all stores. Okay, so this is transform transpose guys. Okay, so transforms perspective of data for different types of analysis. So now we'll have to understand inverse of a matrix. Okay guys, so before diving into inverse or identity matrix, we will see an use case, right? Suppose the price of 2 apples and 3 oranges is $8 and 5 apples and 6 oranges is $17. If I make equation of them, 2x plus 5y equals 8 and 5x plus 6y equals 17, can you solve the problem? So we know how to solve two equations, right? So ChatGPT is solving the problem and it's giving me the result. X equals 1, y equals to 2. Okay, so if you want, you can check if it's okay. So in these equations, if you put values of x1 and y2, then you will get 8. Okay, x1 is 1 into 2, 2, 3 into 2, 6. So 6 plus 2 would be 8. So this will be true as well, right? Now I asked, and now can you write these equations in matrix form? Can you explain inverse identity matrix from this? Also, can you give me the idea of determinant from this? Okay, so my plan is to get all the things clear from this example, right? So the given system of equation is this one. We can represent this in matrix form as so now you can guess how where matrix is applied, guys. Okay, so we always see these types of equations in our books in class 9, 10. Okay, so the same thing can be applied, can be presented in this way. This is the matrix representation, guys. Okay, so when I was in college, I used to wonder what these things are, why we are doing this. Yeah, now we can understand that uh, say simple things can be presented in matrix as well. Okay, so this is in the form ax equals b. Okay, so a means, guys, this is the a vector, you can say, and this is the b vector, right? This is b and this is x vector. So we can write ax equals to b, understanding the inverse matrix. So what is inverse matrix, guys? So we have to understand the inverse first. Okay, so forget the screen now, listen to me now. Okay, so what is inverse, guys? Inverse is related with you can say operation. Okay, so whether it's addition operation or multiplication operation. Okay, so let's say in case of multiplication, in uh, we have to understand the identity too. Okay, so in case of multiplication, identity is 1. Okay, so let's say you took a number 2. Okay, so what is the number uh, multiplied by 2 gives us 1, because 1 is the identity for multiplication, right? So we have to we need to target the identity. Okay, so we need to get identity. So identity is 1 for multiplication. So if you 2 with half, 2 multiplied by half, we will get 1. So half is the identity, half is the inverse for 2 in case of multiplication. Okay, so but in case of addition, identity is 0. So which number is gives us 0 if we add with 2? So this would be -2, right? 2 plus -2, we get 0. So -2 is the inverse for 2 in case of addition, you can say. If you didn't understand, you can rewind the video again. So here you can say understanding the inverse matrix. If a matrix A has inverse, this is how the inverse is presented, and then we can solve x for x equals A inverse B, right? So to find A inverse, we use the formula for inverse 2 into 2 matrix. So this is the formula, guys. This is the formula to find inverse, right? So we will see in our case how it's being applied. So you see here where A equals A, B, C, D, and determinant A is the determinant of matrix A. Okay, so for the matrix A1, so 2 into 6 minus 3 into 5. That means, guys, if you see what is our matrix A, you see 2 into 6, 5, 3 into 5, right? So see this one. So finally we are getting -3. Okay, so since determinant not equals to 0, the inverse exists and we can calculate. Okay, so you see here the inverse exists and we can calculate. So finally we are getting a result. Okay, so finally we are getting x equals to 1, y equals to 2, right? So what would happen if the determinant was 0? We will see this one now. Okay, so identity matrix explanation. The identity matrix is a specific matrix that multiplied by another matrix gives back the same matrix. For 2 into 2 matrix, the identity matrix is this one. Okay, so 1 0 0 1. So why is this, guys? Because identity matrix, we know the 1 is identity for multiplication. So whatever the matrix is multiplied with this, we get that matrix. Okay, so how it's happening, we will see now. Okay, so you see determinant interpretation. The determinant of a matrix is a single number that gives us important information. If determinant is 0, the matrix does not have an inverse, meaning the system of equations might have no solution or infinitely many solutions. So we will see what actually this means and what happens if it's not equals 0. If it's, yeah. So you see here identity matrix, whatever I discussed you, it's here, right? So think of number first. What happens when you multiply any number with 1? 5 into 1 equals 5, 10 into 1 equals 10. The number remains the same because 1 is the identity for multiplication, right? So similarly in matrices, the identity matrix works like 1. For 2 into 2 matrix, the identity matrix is this. So if you see here, if you multiply this matrix with this, you get the same thing, right? Determinant, like the area of a shape. The determinant is a special number that tells us important things about a matrix. For 2 into 2 matrix, you see here, A into D minus B into C. Okay, so it's we have to calculate diagonally. Okay, so example, this one we see minus 3. Inverse matrix, like undoing an operation. Okay, so what is inverse matrix, guys? uh, inverse I discussed you already. Okay, if you have 5, what is the inverse of inverse in multiplication? 1 by 5, because multiplying 5 into 1 by 5 you will get 1. In case of addition, it should be minus 5. Okay, so I asked, show me a case where two equations have determinant 0. So let's take an example where two equations have determinant 0. So two equations with no unique solution. 2x plus 4y equals 8, x plus 2y equals 4. So step 1, write in matrix form. So it's giving me in matrix form. Okay, find the determinant. So finally we get, if you put the values, we get 0. So since the determinant is 0, the matrix has no inverse, meaning the system has no unique solution. What does this mean? The second equation is just a multiple of the first equation. Okay, so if you multiply this by 2, if you multiply first equation by 2, we get this one, but this is exactly the second equation. This means both equations represent the same line. Since both equations describe the same line, there are infinitely many solutions. What if the equations were different? Okay, so 2x plus 4y equals to 8, x plus 2y equals to 5. The coefficient matrix would be the same, so its determinant is still 0, but this time the equation contradict each other. Okay, so you may say that this is 8 and 5, so this might be, okay, but no, because this side is everything is as before, right? This means that we have two parallel lines which never intersect, no solution. So final takeaway, the determinant, if the determinant is 0, it means the equation do not have any unique solution. This happens when the two equations describe the same line or parallel lines. Would you like a geometric visualization of this? Okay. Okay, so not being determinant 0, listen to me carefully, guys. Okay, so not being determinant 0, what does actually this mean? Okay, so only because we checked determinant for these equations, right? If it was 0, then it was not possible to find value x and y. Okay, so what actually we are doing? Let's say in our case, in this case, we are getting 2 apples and 3 oranges in $8 from, let's say, from one store. 2 apples and 3 oranges in $8, and you you went to another store and you got 5 apples and 6 oranges in $17. Okay, so now we are trying to find the value for apples and price for apples and oranges. You understand? So what is the condition? We will buy the same number of apples and oranges from both the stores, 2, 3, 5, 6. Okay, we will spend $8 in the first store and $17 in the second store. Everything would be same: 2 apples, 3 oranges, 5 apples, 6 oranges, $8 and $17. But we will have the same price for apples and oranges for both the stores. So many conditions, guys. Everything will be fulfilled if the determinant is not 0. You understand? This is the benefit of getting determinant not equals to 0, guys. I hope you understand, and pardon my weak English. I am trying to explain things clearly, but maybe for my English it might be little bit difficult to you. Now we will see eigenvalues and eigenvectors, guys. Basic theory. Now we will see a scenario. Okay, so business stability analysis using eigenvalues and eigenvectors. Let's say you are running a small business and you want to predict how sales will change based on past data. To do so, you decide to model the growth of your business using matrices, especially focusing on eigenvalues and eigenvectors. These concepts will help us understand how different sales categories grow in proportion to one another and identify any stable or dominant trends over time. So you have two products. Product one costs $3 per unit, and product two costs $5 per unit. You get the data on how much sales change over time for both products. So week one, you sell 10 units of product one and 15 units of product two. Week two, you sell 12 units of product one and 20 units of product two. In week three, you sell 15 units of product one and 28 units of product two. So you use a transition matrix to model this. The matrix helps you understand how sales of product one and product two evolve from one into to the next. So transition matrix you see here. Okay. So growth of product one, growth of product two, growth of So by comparing the sales over the weeks, product one sales increase from 10 to 12 to 15. Okay, so that means, guys, when it's increased 10 to 12, its growth is 1.2 and then 1.25. Okay, so two growths are here, 10 to 12 and 15. So it's 1.2 and 1.225. So for product two, 15 to 20 to 28. So that means, guys, 1.33 and 1.4. Okay, so these are the growths. So the transition matrix for the growth is 1.2, 1.33. So these are the values for first product, and these are the values for 1.25, 1.4. Okay. Okay. This eigenvalues and eigenvectors. Now we'll understand how these terms come into action, right? Now we want to calculate the eigenvalues and eigenvectors of this matrix to understand the dominant trends and whether there any steady state where sales of product one and product two will stabilize. Eigenvalue, that this represents the growth factor that allows the matrix to have a stable. So you can read this thing, guys. Okay. Now we will see actually how this work. Find the eigenvalues. So determinant into a minus delta I equals 0. Okay, so now we will see what this actually mean, guys. A is the matrix we formed, and delta is the uh, this is the eigenvalue, I will say lambda, and I is the identity matrix, right? So for our matrix A, this one, A minus delta t, delta I equals to, so here dt 1.2 minus lambda. Okay, 1.25, 1.33, 1.4 minus lambda. So just we are replacing the values, guys. Okay, so this gives us the characteristic equation 1.2 minus lambda, 1.4 minus lambda. Okay, so these two, okay, minus, so we know how we determine the determinant, right? So if we calculate this one, if we put basic rules of algebra, then we get this one, right? So now we are calculating the result for this one. So after all the calculations, we get this equals 0. So we solve this equation by quadratic formula. Okay, so I hope you understand what a quadratic formula is. If you don't understand, you can check another video. Uh, you can learn about quadratic formula, or I make another video for this. Okay, so we are getting values for lambda. So finally we are getting two values for lambda, right? You can see here, plus minus, that means two values would be there. So two values is there. So if you interpret the eigenvalues, eigenvalue 1, lambda 1 is 2 point, so two eigenvalues we got. This is the dominant eigenvalue. It tells us the sales growth will be exponentially increasing with the product growing at a rate of this times the current sales. Okay, so from the current sales it will be steadily exponentially increasing. So eigenvalue lambda 2 equals this one. This is a very small eigenvalue, suggesting that the effect of this direction is negligible over time. It may indicate that one of the products, likely product 1 or product 2, will slowly lose importance or shrink in sales. Okay, so there is a possibility that one of the products will get less sales. Okay, find the eigenvectors for lambda 1, 2.595. We solve the system. So if we solve this equation, okay, so conclusion, eigenvalues tell us about the rate of growth or decay in the system. The dominant eigenvalue indicates how fast the business is growing. Eigenvectors give us the direction of the growth, meaning how the sales of different products will change together in the future. So in this case, understanding eigenvalues and eigenvectors helps you predict the long-term behavior of your sales and identify which products will contribute most significantly to the growth of your business. Okay, so it's just to get a rough idea. Okay, everybody, now we will see some vector practice problems. Okay, so our first problem is business profit analysis. So you can see here a company has two stores. The profit from store A and store B in 3 months is given by vectors A 10, 15, 20. Store A profits for January, February, March. Store B 12, 18, 25. Store B profits for January, February, March. Okay, so question is what is the total profit from both stores for each month? So these are will be just added to 10 and 12, 22, 15 and 18, 20 and 25. So if you add them separately, you will get the profit, right? Total profit. And if the company decides to double its advertising budget and they expect each month's profit to increase by 1.5 times, what will be the new expected profits for store A? So that means with all the values, with all the profits of January, February and March for store A, okay. So in the values of store A, 1.5 would be multiplied with all the profits, right? Each month's profit. So whatever the result we will get the answer, right? Okay, so second problem. A delivery driver travels 3 kilometer east and 4 kilometer north from the starting point. So question is, how far is the driver from the starting point? Find the magnitude of the displacement vector. And if the driver now moves 6 kilometer east and 8 kilometer north, is this movement in the same direction as the first one? Okay, so these are the two questions we have to solve. So if we want to know the distance from the starting point, simply we will have to find the magnitude, right? So the magnitude of a vector, this one, v, so 3 square plus 4 squared, okay, and you get 9 plus 16 root over 25 equals 5 kilometer, right? So the driver is 5 kilometer away from the starting point. So checking the second movement is in the same direction. Two vectors are in the same direction if one is a scalar multiple of the other. Okay, so if you see here 6, 8, okay, 6, 8 was our new point, right? And what we had is 3 and 4. So if you multiply 3 by 2 we get 6, multiply 4 by 2 we get 8. So this is just simple. You can say that these values are being multiplied by 2 directly, right? We can say that. So since both values of k are the same, the second movement is in the same direction as the first one. Yes, the second movement is just towards the first one, so it's in the same direction, we can say. Now we have another problem, that is sales tracking, right? A matrix addition. A shop records the sales of 3 products, P1, P2 and P3 over 2 weeks in the matrices. 50, 30, 20. So you can see here, right? So each row represents a week and each column represents a product. Find the total sales for both weeks. If the price of each product is $5, $10 and $15, find the total revenue for each week using matrix multiplication. So you can see the matrices here, right? So if we see the solution, total sales for both weeks, right? So metric addition is done by adding corresponding elements. So 50 plus 60, 30 plus 45, 20 plus 30, right? You can see here 50, 60, 30, 45, 20, 30, 40 plus 50, 35 plus 40. So this is how it will work, and you can see the result, right? So total sales for both weeks is week 1 110, 75 for 50 P3 week. So you can see the results here, right? So total revenue for each week. So price matrix is 5, 10, 15, as we've seen before, and this all the values will be multiplied by these, right? 5 into 50 into 5, 30 into 10, 20 into 15. So you can see here for week 2, 14 to 5. So I hope you can guess the result, guys. Okay, you can see the result here. We have another problem, that is employee salary calculation, a scalar multiplication. Okay, so a company pays its employees based on their working hours. The number of hours worked in a week is 40, 35, 45, 30. Okay, so the hourly wage for two employees are 20 and 25. Questions. Number 1, compute the weekly salary of each employee using scalar multiplication, right? Weekly salary of each employee using scalar multiplication. This is very easy, guys. Scalar multiplication is performed by multiplying each employee's working hours by their respective hourly wage. Okay, so for employee 1, it's all the things will be multiplied by 20, right? So we get this result. And for employee 2, we get multiplying by 25, right? So you can see the results here. Our next problem is product sales projection. A store sells 3 products, P1, P2, P3 in 2 cities. The number of units sold is this. Okay, the price per unit product is this. So find the total revenue from each city using matrix multiplication. So this thing would be easy, guys, right? So this is the matrix. Each row represents a store and each column represents a product. The profit per unit, this 15, 10, 15, 5, 10, 15. So each row corresponds to be the profit per unit. Compute the total profit for each store using matrix multiplication. So S into P, that means this into this. If we multiply 20 into 5, 15 into 10, and plus 10 into 15, okay, so we get 400 for store 1 and 725 for store 2. Okay. Okay, the next problem we have is a business stability check. Determinant of a matrix. A company has the following matrix representing the relationships between two products, supply and demand. Okay, so this is the matrix. Compute the determinant of the matrix. If the determinant is 0, what does this indicate about business stability? Okay, so we need to see this answer, guys. Okay, so you can see the solution here. Okay, a determinant of a matrix and business stability. We are given the supply demand matrix here. Okay, so compute the determinant of matrix M. So we know the formula, right? So that means, guys, A into D minus B into C, right? So here in our case 3 into 4 minus 5 into 2, so 12 minus 10 equals 2. Okay, so this is not 0, guys. If determinant is 0, then it's not possible to get any solution, we know. But in our case, since determinant M not equal to 0, the matrix is invertible, meaning the supply and demand relationship is stable. So business stability interpretation, if determinant is not 0, the system is stable. This means that the relationship between two products, supply and demand, is independent and well balanced. The company can predict and adjust supply based on demand without major issues. If determinant is 0, the system is unstable. This would mean that the supply and demand of one product are directly dependent on the other, leading to redundancy in business decisions. Okay, it could indicate insufficiencies or lack of flexibility in adjusting to changes. So guys, now we have the last problem, and that is solving for prices. Okay, so inverse of a matrix. A store sells 2 types of fruit baskets. Basket A contains 2 apples and 3 oranges. and basket B contains 1 apple and 2 oranges. If the total cost of basket A is $10, and basket B $6, set up the system of equations and use the inverse of a matrix and to find the cost of 1 apple and 1 orange. Okay, so we need to make equations and calculate, right? Okay, so we are given two fruit baskets. Basket A contains 2 apples and 3 oranges and costs $10. Basket B contains 1 apple and 2 oranges and costs $6. Our goal is to find the price of apple and oranges. So set up the system of equation. X equals, okay, so 2x plus 3y equals 10. 1x plus 2y equals to 6. So now we can organize these informations like this, right? According to matrix. So A is 2, 3. This is the A matrix. This is the X, and this is B. Okay. So compute. Okay. So we need to find the determinant. 2 into 2 minus 3 into 1. So determinant is 1. Since it's not equal to 0, the inverse exists. Okay. As inverse exists, you can say inverse is this one. Okay. So solve for X. So X equals A inverse B. So you see here. And we get the values of X, ultimately 2, y equals to 2, right? So if you want, you can check these values. Okay, you can substitute the values of X and Y in the equations, and you can check if we get proper, I mean the equations uh, proves true, right? So the price of 1 apple is $2 and price of 1 orange is $2. Okay, so these are the problems we could see, guys, for now. Okay, so I hope you could get a good idea about the things. Yeah, so as a short course, or maybe within 1 or 2 hour, it's not enough to study about this. You have to we have to spend more time, but we get you get a good idea about the topics, right? So we will move to the next. Okay, everybody, and now we will try to understand little bit more about eigenvalues and eigenvectors, right? So in simple terms, given a square matrix A, an eigenvector V is a non-zero vector that only changes by a scalar vector multiplied by A. So AB equals lambda V. We saw these things before, right? So A is n into n matrix. That means square matrix, right? And V is the eigenvector. Lambda is the corresponding eigenvalue. This means that instead of changing direction, the vector V is simply stretched or shrunk by the lambda. Anyway, guys, finding eigenvalues, we know that determinant A minus lambda I equals 0. So where I is the identity matrix of the same size of A, right? So let's consider the matrix 4, 2, 1, 3, and determinant minus lambda. This one we know, identity matrix, and 4 minus lambda. You see here, expanding the determinant. I see the calculation, right? 4 minus lambda, 3 into 3 minus lambda, and after factoring we get this. So the eigenvalues are lambda 1 equals to 5, lambda 2 equals to 2. So finding eigenvectors, for each eigenvalue we solve A minus lambda IB equals to 0. So A minus lambda means 5, right? 5I. So you see here, okay, 4 minus 5, 3 minus 5. So this is the thing we get setting up the system. From the first row we get x equals to 2y. Choosing y equal to 1, we get x equal to 2. So solve the eigenvector is 2, 1. For lambda 2 equals to 2. So you see here, A minus 2y, okay, 2x plus 2y, x equal to minus 1. So v2 equal to minus 1 by. So geometric interpretation, eigenvectors represent direction in which a transformation acts by only one scaling the vector. Eigenvalues tell how much the eigenvectors are stretched or shrunk. For example, if an eigenvalue is positive and greater than 1, the vector is stretched. Between 0 and 1, the vector is shrunk. Negative, the vector is flipped. 0, the vector is collapsed or collapsed to 0. Okay. You see summary here, application, PCA, principal component analysis, eigenvectors of the covariance matrix help in differential equations, Google page rank. You can see here, okay, summary. Eigenvalues are scalars that indicates how much an eigenvector is stretched or shrunk by transformation. Eigenvectors are non-zero vectors that don't change direction under the transformation. To find them, we have these formulas. Now I will, so why, okay, I have asked some question here, okay, so this is, maybe you will not understand this. Why 4 minus lambda and 3 minus lambda, why not 1 minus, okay. So that means, guys, if I show you, you see here, okay, so I just asked why 4 minus lambda and 3 minus lambda, why not lambda with them, or okay. So as you know, as a new learner, things seems sometimes quite difficult, and sometimes you get confused with the same thing, right? So ChatGPT said, a good question. The reason we subtract lambda from the diagonal elements 4 and 3 in this case, rather than from all elements, is because we are dealing with that characteristic equation which comes from the determinant of matrix A minus lambda I. So step by step explanation, we are given a square matrix, this one, and to find the eigenvalues we need to solve this, right? So why I is the identity matrix, I equals 1 0 0 1, okay, so lambda I equal this. Now subtract lambda I from A, right? So A minus lambda I, that means this one, guys, 4 2 lambda 0, okay. So now you can see, if you subtract, okay, subtract according to the uh, formula, we get this value, right? We subtract lambda only from the diagonal elements, 4 and 3 in this case, because the identity matrix has ones on the diagonal and zeros everywhere else. The subtraction occurs only at positions where I has non-zero elements, okay. So we subtract lambda from the diagonal elements because the eigenvalues come from solving. Anyway, you can see the same thing here, guys, okay. Introduction to singular value decomposition, SVD, okay. This is quite advanced topic, but we will try to understand easily, guys, okay, as easy as we can. I don't have experience working in a big company, and if you're new, then you just can get some idea about the things, okay, so that you can at least get some knowledge about these things. So singular value decomposition, SVD, is a powerful mathematical tool used in linear algebra. It is widely applied in machine learning. So what is SVD? Given an m into n matrix A, SVD factorizes into the three matrices, okay. So that means uh, with the help of three matrices we get SVD A, right? So U is an m into m, that means it's a square matrix, orthogonal matrix. This this is m into m, diagonal matrix, singular values, and Pt is an n into n. Okay, so breaking down the component, singular values, the matrix, we call the summation, contains regular values along this diagonal. Let's see what actually this mean and how actually this is applied, okay. Example of SVD, let's say we have a this matrix. Computing SVD by by hand is tedious, but computational tools like Python's NumPy can do it easily, right? So you say we get you this summation, this VT. This means that A can be written as uh, like this, right? So which helps in analysis, compression, and transformation. And summary, SVD decomposes any matrix into three special matrix. This one, and singular value in summation in determine the importance of components, applications, data science, machine learning, image processing, and more. Okay, so give me real life scenario where SVD is used. If you can give me, okay, so real life buy and sell scenario as we've discussed before. So online marketplace like Amazon, Flipkart, etc. Imagine you own an online shopping platform and you want to recommend the best product to customers based on their past buying behavior, right? So collecting data, you have a purchase history matrix here. Rows represents customers, column represents products, and values represents how much a customer likes a product. Okay, so let's say we have this matrix, and row one, I mean customer one, customer one's value is for the row one, right? Gives a product. The first product is giving 5 star rating, and second product, 4 star rating. Third product, the customer didn't make any comment or like it. Okay, didn't give any reaction. And for the fourth product, the customer one has given 1 star only. Okay, you can say for customer three. So these are the data for different customers. Okay, so applying SVD, you see SVD breaks this one. So U captures customer preference. Okay, customer's preference. U summation contains singular values, importance of different features, and VT captures product similarities and features. Okay, so making recommendations, buying and selling impact. The missing values in the matrix represent products that as a customer hasn't interacted with yet. Using SVD based matrix approximation, we can predict which products a customer is likely to buy. Okay, so for example, if customer 2 has bought product 1 but never saw new product 3, SVD might recommend product 3 based on their similarity. Okay, if a seller wants to introduce a new product, SVD helps predict which customers are most likely to buy it. So we, in our real life, we face this thing again and again in life, right? Let's say we've purchased something from a website, and sometimes we see this similar kind of products are in our news feed, right? So maybe this SVD comes into action when engineers make some things so that we get these types of suggestions, right? SVD is widely used in recommendation systems like Amazon, Netflix, and Spotify. By breaking down complex, okay, so anyway, you can see this, and ChatGPT is recommending me if I want a Python code. So I said yes, I want a Python code, and if you want, you can see this code as well. So maybe as a new programmer or maybe as a new learner, things would be hard for us to understand, but we will try at least. Okay, we will just see a demo, right? So you see the code here. If you want, you can see this. What this means: simple customer product matrix, a row customers column equals products, right? So now SVD reduced to two latent features. Apply SVD, reconstruct the matrix approximation, display original and reconstructed matrix, function to recommend top products for a customer, uh, and you see that. So I told ChatGPT is giving me the explanation here, matrix representation. Each row represents a customer, right? You can read here, right? Take some time to read this. Simple output, original rating matrix is this, predicted ratings matrix, this one, recommended for customers 2, product 3, predicted score 1.02, product 2, product 3, product 2. Okay, so what did we achieve? Missing values, zeros are predicted using were predicted using SVD. Customer 2 who hadn't rated product 2 and 3 is now recommended product 3 first. This method is used by Amazon, Netflix, and YouTube to suggest products, movies, or videos. Would you like to try this with real data? Okay, explain me the code line by line. I said to explain it. So you see, import necessary libraries. So Python's inbuilt libraries or modules are being imported here. So you see NumPy and sklearn.decomposition import truncated SVD NumPy. So if you have enough idea about this, okay. So define the customer product rating matrix you see here, and applying SVD. Okay, so reduce to two important features. Okay, so two important features is being stored in this SVD variable, right? Because we have so many features, so we're not considering everything, because we don't need, we want to choose a specific customer, right? So if we just gather the important features, okay, if we consider the important features, then it would be easy to find the most important products or most important recommendation. Okay, so reconstruct may reprint original product, okay, and definition to function recommend products. So now we have another thing to learn, and that is PCA, okay, principal component analysis. I explained this topic as you discussed SVD. So you see here principal component analysis, just like singular value decomposition. Principal component analysis PCA is a powerful mathematical tool used for data dimensionality reduction and feature extraction. It is widely used in, okay, so why you can see, you can pause the video and you can read if you want. Okay, so why use PCA? You can see here, when you have data in the form of multiple features, reduce the number of features while retaining most of the important information, make the data easier to analyze and visualize, remove correlations between features. For example, if you have a data set with thousands of features, we might want to reduce it to a few features that still represent the underlying structure of the data. Okay, so PCA is in simple terms. Imagine you have a data set with lots of dimensions, but those dimensions might be correlated with each other. You can read this, okay. We have the mathematical formula here. Given a data matrix X, where each row is a data point and each column is a feature. Okay, center the data X minus mean X. Okay, calculate the covariance matrix. Find the eigenvectors and eigenvalues of the covariance matrix, where V is an eigenvector, principal component, lambda is the eigenvalue. Sort the eigenvectors by their corresponding eigenvalues in descending order. Project the data. A real life example of PCA. So this is what we are looking for, guys. Okay, so we are just trying to gain some knowledge about this. Okay, so imagine you are an e-commerce company and you have a customer data like age, income, number of purchases, rating of products. Okay, so problem, you have a lot of features and some of them are highly correlated. For example, age and income might be strongly related. You want to reduce the number of features while keeping the important patterns that describe your customers. Okay, so using PCA finds the main axis where the data varies the most. It may find that the first principal component captures the relationship between age and income, and the second component captures the purchasing behavior. By keeping only the top 2 and 3 principal components, you can reduce your feature set and use this. Okay, so why PCA works so well? Dimensionality reduction. By projecting into few dimensions, PCA helps in reducing the number of variables without losing important information. Noise reduction, it helps in reducing noise, okay, in the data, focusing on larger pattern visualization. Okay, comparison to SVD. SVD is the mathematical method used to perform PCA. In fact, PCA can be implemented using SVD on the covariance matrix. SVD and PCA are closely related. PCA can be seen as a specific case of SVD used for dimensionality reduction. So we've got another code for PCA, right? Like SVD, important numpy as NP. You see here, these are the inbuilt method function. Simple data, each row represents, this is the matrix, customer 1, customer 2, 3, 4, standardizing the data, print the transformed data. I hope you got a little bit idea about this, guys. Okay, I'm sorry I couldn't give you a proper idea, as I am not an industry person, but I tried to explain the terms, what they are, how they can be applied. Okay, I hope it would be at least useful to you guys. Okay everyone, now we will see most important topic of linear algebra, and that is matrix factorization. Okay, so we will directly see a real life scenario, and then we will try to explain these things, right? So you can see in my screen a business scenario. Okay, predicting customer preferences in a marketplace. So scenario, an online retail store. Imagine you own an online store that sells gadgets, and you want to understand which products customers like based on their past purchases. However, customers don't buy everything, so your data set is incomplete, right? So the data, customer product purchase matrix, you have a customer product matrix where rows represents customers, column represent products. Okay, each cell contains a rating between 1 to 5. Okay, so here's an example. Customer product Elise, give the smartphone 5-star rating, tablet 3-star ratings, and smartwatch 4 stars. Okay, and about laptop and headphone, maybe he didn't buy, or maybe he didn't want to respond something. Okay, in case of Bob, it's for laptop it's 4, headphones is 5, and so on. Okay, so problem, there are missing values. So missing values are indicated by the question mark, because customers don't rate or buy every product. Okay, how can we predict what a customer might like and recommend products to them? Okay, solution, using matrix factorization for recommendations. Okay, so using matrix factorization, we can approximate the missing values by decomposing the matrix into two smaller matrices: customer feature matrix, product feature matrix. Okay, so U and V. Okay, so these matrices capture hidden customer preferences and product similarities. The goal is to fill in the missing values to predict what customers might like. Steps to apply matrix factorization: decompose the matrix. We factorize the customer product matrix into, okay, so A equals U, U cross B. Okay, U product B. So U represents customer preference features, and V represents product features. So do we train the model, use singular value decomposition or non-negative matrix factorization to learn these matrices, optimize them by minimizing the difference between known ratings and predicted ratings, predict missing values, multiply U and V to reconstruct the original matrix with predicted values. Anyway, the practical application, so this is the A matrix. Okay, let's take a small customer product matrix, A matrix. Using matrix factorization, we decompose it into two matrices, right? So this is U and this is V. So when you multiply this, okay, so 1.2 into 1.7, 0.7, 0.8 into 1.3, right, and so on. So 1.8, 1.2 would be 1.1 multiplied by 1.1, and 0.8 into 0.8. So 1.2 would be again 0.9, and 0.8 would be would be multiplied with 0.6. So for 0.9 and 0. 1.1, 1.5 or 0.7, so there will be two more rows like this, right? So okay, so this reconstructed matrix contains predictions for their missing values. Benefits in business: personalized recommendations, suggest products that customers are likely to buy based on their past purchases. Example, if Elise liked smartphones and smartwatches, she might also like tablets. Demand forecasting helps predict which products will be in high demand. Example, if multiple customers show interest in certain product, stock more inventory. Okay, so customer segmentation, group similar customers based on their buying habits. Example, identify budget conscious versus premium customers and create targeted marketing campaigns. Fraud detection, detect unusual purchase patterns that might indicate fraudulent activities. Okay, so conclusion: matrix factorization is a powerful tool for business analysis. So, especially in recommendation system, customer insights, and product demand forecasting. By breaking down large data sets into meaningful patterns, businesses can improve customer experience, increase sales, and optimize inventory. So, last three topics. Okay, this one, matrix factorization, SVD, and PCA. So these were advanced things, and we have to study more about these. Uh, okay, so use YouTube, use ChatGPT as much as you can, and try to learn about these things. Okay, so this video is over here, and try to solve some problems related to linear algebra. I showed as much as I could. We need calculus 2, right? So see you in some other video. Thank you for watching this video, and if you like my content, please subscribe my channel and share with your friends. Okay, and please like, comment, and let me know how you like it, or if you don't like, please let me know. Thank you.